Welcome to lecture 4.4 in college algebra, theorems about zeros of polynomial functions. Today we're going to focus on how to find a polynomial with specified zeros. And for a polynomial function with integer coefficients, we're going to find the rational zeros and other zeros if possible. And we're going to skip Descartes' rule of signs to find information about the number of zeros, so don't worry about that part. Every area of math, every subcategory of math has a fundamental theorem. And the fundamental theorem of algebra states that every polynomial of degree n, remember that's the largest exponent, a quadratic is a degree 2, a cubic is a degree 3. Every polynomial function of degree n with n greater than or equal to 1 has at least one zero in the system of complex numbers. Okay? So remember that a zero is where a graph crosses the x-axis. So, we've seen quadratic equations where the parabola is all above or all below the x-axis. So it doesn't have any real zeros, no real numbers that are zeros, but it would still have at least one complex. Remember the imaginary numbers, 4 plus 3i, etc. But it would still have, even if it doesn't cross the x-axis, it still has at least one zero in the set of imaginary, really, or complex numbers. Find a polynomial function of degree 4 having zeros 1, 2, 4i, and negative 4i. Now remember, when we know where the zeros are, we know that, for example, if the zero is at 1, then this factor is x minus 1. The factor for when there's a 0 at 2 is x minus 2. At 4i, x minus 4i, and at negative 4i, it would be x minus a minus 4i, or x plus 4i, okay? So such a polynomial has factors x minus 1, x minus 2, x minus 4i, and x plus 4i. So we have a sub n. This is just any constant multiplier, any kind of coefficient, times those four factors multiplied together. If we set a sub n equal to 1, then and multiply this out by foiling, and then multiplying, distributing, or using the box method, we get x to the fourth minus 3x cubed plus 18x squared minus 48x plus 32. And that's just, again, foiling the first two terms here, the second two terms here, and then multiplying them through using distribution. Okay, I'm not going to go through those steps. You should be able to do that, and you can try it with this problem to make sure that you understand how to multiply through. And take your time and make sure that you don't miss any. A multiplication table is a good idea to move from this step 2 to step 3. Do 3 boxes across the top, 2 along the side, and on the top put x squared, then minus 3x, and then 2, and on the side put x squared and 16, and then just, as in a multiplication table, what goes inside the box is the product of what's on the outer edges of the box, like you did in elementary school when we were learning our times tables. Zeros of polynomial functions with real coefficients. Non-real zeros. If a complex number, a plus bi, where b does not equal 0, is a zero of the polynomial function f of x with real coefficients, that just means a and b are numbers, then its conjugate, remember conjugates are one's a sum and one's a difference, a minus bi is also a zero. Non-real zeros occur in conjugate pairs. For example, if 4 plus 3i is a 0, then 4 minus 3i is a 0. And remember, we're not changing the sign of everything here. We're just changing the operation from plus to minus or vice versa. We're not changing the polarity or the sign of the first digit. For irrational zeros, if a plus c times the square root of b, where a, b, and c are rational and b is not a perfect square, is a zero of a polynomial function f of x with rational coefficients, then its conjugate, a minus c times the square root of b, is also a zero. Okay? So again, if we had 4 plus the square root of 7 is a 0, then 4 minus the square root of 7 is a 0. So both non-real zeros and irrational zeros occur in pairs, in conjugate pairs. And again, it's important to remember, we're not changing the sign of everything. We're just changing the operation from plus to minus or minus to plus. Suppose that a polynomial function of degree 6 with rational coefficients has negative 3 plus 2i, negative 6i, and 1 plus the square root of 2 as 3 of its zeros. Find the other zeros. The other zeros are the conjugates of the given zeros. So we get, for the first zero, we get negative 3 minus 2i because we had plus 2i. A negative 6i, this is like 0 minus 6i. So we get plus 6i because this is like 0 plus 6i or positive 6i. 1 plus the square root of 2, its conjugate is 1 minus the square root of 2. And so those are the other zeros. And it can't have any more because it's degree 6. And the most zeros a degree 6 can have is 6. This is probably the most complicated part and confusing part of today's lecture. And it's the rational zeros theorem. Let p of x equal a sub n x to the n plus a to the sub n minus 1 x to the n minus 1 dot 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 a2 x2 x squared plus a sub 1 x to the power of 1 plus a sub 0, where all the coefficients are integers. Consider a rational number denoted by p over q. A rational number is just a fraction, where p and q are relatively prime, having no common factors besides 1 and negative 1. If p over q, if this fraction is a 0 of p of x, then p is a factor of a sub 0. You see it bold and black at the end. And q is a factor of a sub n, which is the coefficient on the leading term. This is a way to find all possible zeros using the lead coefficient and the constant at the end. Okay? We're going to see how to do that in just a second. So that's all this rational zero theorem is notice we have p over q. P has to be a factor of a sub 0, and q has to be a factor of a sub n, the leading coefficient. Given f of x equals 2x cubed minus 3x squared minus 11x plus 6, find the rational zeros and then the other zeros, then factor f of x into linear factors. Okay? So let's first look at figuring out all the possible factors, all the possible zeros for f of x. The way we do that, remember, it's p over q, and q is made up, the numerator has to be made up of the factors of a sub 0, which is 6, and q has to be made up of the factors of a sub n, which is the leading coefficient, the coefficient in the leading term, which is 2. So if we kind of combine all of those, so the possibilities for p are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, because those are the factors of positive 6. Positive 1 times positive 6, negative 1 times positive 6, positive 1 times negative 6, 2 times 3, negative, etc., etc. Okay? For 2, there's only 2 factors, right? 2 is equal to 1 times 2, and it can be either positive or negative. Now, to find the possibilities for all the zeros, what we do is we have to figure out all the combinations. So we get 1 over 1, which is positive or negative 1, because we can change the sign. And 1 over 2, positive or negative 1/2. 2 over 1, which is positive or negative 2. And 2 over 2, which we already have because 2 over 2 is 1 or negative 1. 3 over 1 gives us 3 or negative 3, and 3 over 2 gives us 3/2 or negative 3/2. 6 over 1 gives us 6 or negative 6, and 6 over 2 gives us 3 or negative 3, which we already have. So we know that our zeros are one of these, looks like about 6, about 12, 6 pairs or 12 different possibilities. So what we're going to do now is just basically do trial and error to find our zero. The best way to do this is to go ahead and use synthetic division. We could just plug these values in and see which one equals 0. Remember that when we do synthetic division, the remainder is equal to the functional value. So we could just plug these in, but if we go ahead and do the synthetic division, remember that if we get a 0 remainder, then we've already got one factor, which was our original answer, x minus c, and the other factor is the result of the synthetic division, which will make it easier to continue to factor until we have only linear factors. So let's look at a problem, let's continue this problem. So I've put up here, I reminded you of the function f of x and of all the possibilities, the 12 possibilities. So we're going to try 1, -1, and 3 until we hit 1. So remember that for synthetic division, if we're going to use 1, then the 1 will be our x, because this is a factor of x minus 1. And then we'll be dividing that into 2, -3, -11, 6. Okay? I'm not going to go through this. Remember, we just bring the first term down, multiply, add, then multiply, add down, multiply, add down. But we can see here that we do not have a remainder of 0 when x equals 1. So x minus 1 is not a factor. So we try -1. This is x plus 1. The x is -1. We use the same coefficients. Bring the first term down, multiply through, add down, multiply through, add down, multiply through, add down. And again, we see that we do not have a 0 for a remainder. So neither x equals 1 or x equals -1 are a 0. Neither of these are factors, x minus 1 or x plus 1. So let's try 3. Let's just keep going until we find one. Again, 3, this is x minus 3 is the factor. And then, of course, we're going to use the same. We're going to divide that 3 into 2, -3, -11, and 6 from the original function. Again, bring the first term down, multiply through, we get 6, add down, multiply through, add down, multiply through, add down, and we get 0. So this is telling us that 3 is a 0, thus x minus that 0 is a factor. But the good part here is we also know what the other factor left is because we did the synthetic division. Remember, these are the coefficients on the polynomial, and it's 1 degree less. So we have 2x squared plus 3x minus 2. 2x squared plus 3x minus 2. Remember, the quotient is 1 degree less than the original function that we're dividing into. Well, we can factor this 2x squared plus 3x minus 2 using the AC method as 2x minus 1 and x plus 2, which this then gives us our factored form, our first factor x minus 3, and then our two subsequent factors of the quadratic, 2x minus 1 and x plus 2. So we've answered the first question, which is to factor it, and then we want all the zeros. Well, we can see that there's a 0 at 3, a 0 at -2, and then here we get a 0 at 1/2 by setting them each equal to 0. Okay, so today's lecture is pretty short. That's the end of it. It's just how to find all the possible zeros and factor complicated polynomials using synthetic division.